Okay, so let's start with some more examples of collision of particle with a surface. Just a second. Luko, come here. Stop moving. Come here. What happened? Okay, so let's see this example. So what we are observing is that we drop a particle onto a inclined surface, fixed inclined surface like this. And the fixed inclined surface is at theta to the horizontal. This theta is 37 degrees. Now we drop the particle from a height of 20 meters. And what we observe is that immediately after the impact, the particle has the velocity which is horizontal. So after impact, just after impact, it develops a horizontal velocity. So the velocity, the impact or the collision impulse acts in such a way that the final momentum just after the impact happens to be horizontal. Whereas, as you can see, the impact velocity will happen to be vertical because we just dropped it from that height. Okay, so given this situation, we have to calculate firstly how much this horizontal velocity will be. And we have to also calculate the coefficient of restitution, taking the value of g as 10 per second square. So a particle dropped from a height h equal to 20 meters onto this inclined surface makes an oblique collision such that just after impact, okay, so immediately after impact, just after impact, its velocity is horizontal. So from all this information, we have to figure out that what is the horizontal velocity's magnitude. And what is the coefficient of restitution for this particular collision. You just try this question out, people will discuss soon. So you have to work out the geometry of the question here. You have to understand that the vertical velocity of impact will have a normal component and a tangential component. And then you use just that concept that the separation velocity, okay, becomes equal to E times the approach velocity. And the tangential component of velocity remains conserved in an oblique impact. So accordingly, you have to figure out how much this horizontal velocity V just after impact will be. Okay, so let's start with this. Can you tell me how much the impact velocity is? How much is the magnitude of the impact velocity with which it hits? Anyone? Free fall through a
For
height at, yeah, how much?
20 meter per second.
Yes, very good. Root 2 GH, that will be 20 meters per second. Okay. Now, for that impact velocity, what is the normal component going to be? It is that V or V naught, let's say V naught is root 2 GH. So the normal component will be how much? It will be the cos component, cos theta. And the tangential component will be the sine theta component.
Yes.
Okay, so that way you will see now the approach velocity, which is the normal component, will become 20 cos 37. So that is going to be 16. Okay, and the tangential component will be 20 sine 37. That is going to be 12. Okay, now after impact, if the velocity is horizontal and it's V, then now how much is the normal component? It is V cos theta, and the tangential component is V sine theta. So now connect the two by using the concept that separation velocity is equal to E times approach velocity, whereas tangential component of momentum is conserved. So try this out.
Can you repeat?
Yeah, if you just go back to the previous lecture, what we learned that in an oblique collision, the separation velocity is the normal component of velocity, and that is equal to E times the approach velocity, whereas the tangential component of momentum is conserved because the impulse is normal. Okay, so the component of velocity parallel to the surface or tangential to the surface, that remains conserved, whereas the component of velocity perpendicular or normal to the surface, that gets reversed in direction, and that gets multiplied by the factor of E, which is the coefficient of restitution. You understood this? Very good, Adinath. Your answer is correct for both the things, V as well as the coefficient of restitution. Okay, people, let's solve this question fully now. So first of all, let's understand the concept of collision that we'll use over here. So what we had learned last time, just take a quick recap of that, that if a particle hits any rigid surface like this, such that on impact, its impact velocity is like this, let's say, along this line. So it is making an angle theta, let's say, with the normal. So here, the normal component or the perpendicular component of velocity, which is V naught cos theta, that becomes the approach velocity. And the tangential component, that is V naught sin theta. Now, what happens is after impact, suppose the particle goes off with a velocity like this, is along this line, such that this angle is phi. Now we can see that after impact, the normal component, that is V cos phi, so that becomes our separation velocity. Okay. And the tangential component, that is V sin phi. Now, because the collision impulse acts only in the normal direction, the impulse acting on the particle is normal. So therefore, what happens, that tangential component of momentum is conserved. Okay, so mv naught sin theta is equal to mv sin phi. Okay, so that gives us the first result, that v sin phi, this component, is equal to v naught sin theta. And because we define coefficient of restitution, occasion, so because we define coefficient of restitution as ratio of separation velocity to approach velocity, so we have separation velocity is equal to E times approach velocity. So over here, what happens, V cos phi becomes E times V naught cos theta. This becomes our second equation, where in general, you know that E can be anything between 0 and 1. And E is equal to 1 is the perfectly elastic case, and E equal to 0 is the perfectly inelastic case. So this is the concept that we have to apply in this particular question here. Just make sure you understand how these two equations have come. Then we'll see how we apply it to this particular situation. Okay, so let's see how we will implement this concept into this question here. So as I'm sure all of you have realized by now, the impact velocity that is coming from, just you can apply work energy or kinematics or whatever, free fall to a height of h. So the velocity of impact will be √2gh. So numerically that will work out to be, because h was 20 meters. So if the object started from rest over here, fell through a height of 20 meters, then by the time it impacts the surface, it's picked up a velocity of √2gh in magnitude and direction being vertical. So the impact velocity here is like this. So V0 is 20 meters per second. Now for this impact velocity, we have to figure out what is the tangential component and what is the normal component. So this is the normal line, which you are very used to from Newton's laws of motion to the inclined surface. So this angle is theta. So you can see that this V0 cos theta, this is our approach velocity. And that is becoming equal to 20 into cos 37. So that is becoming 16 meters per second. So our approach velocity is 16 meters per second. Whereas V0 sine theta, that is our tangential component. And that is 20 into sine 37, which is 3/5. So that is becoming 12 meters per second. Okay. Now what is going to happen is that immediately after impact, we are given that the particle goes off in what direction? In a horizontal direction. So whatever the horizontal velocity's magnitude is, again, based on that V, we can figure out how much is the tangential component and how much is the normal component. Okay. So all we have to do is understand that. So immediately after impact, the velocity of the particle, let's say, has become V like this. So this is just after impact. So this time we can see that this angle is theta. So the normal component is the sine component of V. Okay, this is the normal axis. Okay. So V sine theta, that is our separation velocity, because this is the normal component. So that is becoming V sine 37 or 3/5 V. Whereas the tangential component, this is our tangential component. So now we connect these two things here, that separation velocity should be equal to E times approach velocity. So from here, separation velocity is 3/5 V, approach velocity is 16. So we'll find the value of E and V. There are two unknowns in this equation. Whereas we also have that tangential component is conserved. So because it is conserved, whatever the tangential component here, that should be the same as here. So V cos theta should become V0 sine theta, or this is V cos 37, 4/5 V. So 4/5 V should be equal to, from here, 12. So that's our second equation, which is coming from conservation of tangential component of momentum. So we have two unknowns, V and E, and we have two equations now. So from the second equation, you can see that V is coming out to be 15 meters per second. Substitute that in the first equation, and you can see the coefficient of restitution will come out to be 9/16. So E is less than 1. You can also see that there is final kinetic energy is less than initial kinetic energy. Okay, so there is loss of kinetic energy because E is less than 1. Okay, so this is another application example of collision of a particle with a rigid surface. Then, for example, if this is a paragraph question, it can go on to ask you the range of the projectile motion that will happen with respect to the inclined plane and all that. So it can be a multiple concept question that along with this, you have to also use projectile motion concepts to find out how it will land somewhere over here after the impact. But here, right now, we are concentrating just on the collision part, so I won't get into that. But you can do that as a homework exercise. You can solve the rest of that later. That after this impact, what happens? Okay, so hope this question is fully clear. Now let's move on to the next part of collisions. In fact, the final part of collisions, where we will see oblique collisions of two particles instead of collision of particle with rigid surface. Earlier, we have seen head-on collision of two particles. Now we will see oblique collisions. That means the collision is not happening along a straight line. This sort of situation. So just for example, suppose we have two bodies which are moving like this. Let's say this is u1, the velocity of the body m1 before impact, and let's say this is u2. And it so happens that the values of u1 and u2 are such that values and also where they are placed initially, they are such that it means that they are eventually going to collide somewhere. Let's say after a bit of time, they're going to come in contact like this. Okay. And as they come in contact, they will apply impulse on each other, this sort of direction. And as a result of that impulse, they will now set off with some final velocities which are in this sort of directions. So this kind of situation. So in any oblique collision, what will happen is momentum conservation will give us a vector relation now. M1 U1 vector is plus M2 U2 vector is equal to M1 V1 vector plus M2 V2 vector. So this is a vector relation which has to be solved using component algebra. So that is what this type of situation is all about. It's about solving momentum conservation equations in component form, because we have to solve them as vector relations now. Because the collision is not happening along a straight line, or it's not a head-on collision. So we will start with a quick, simple example of the application of this. So M1 collides with a stationary body of mass M2 as shown, such that after impact, M1 is deflected by 90 degrees, and final velocity is V1, and M2 is deflected, or M2 starts moving at velocity V2, such that V2 is at 37 degrees with respect to V0. So now, given that V0's magnitude is 12 centimeters per second, or let's make it 15 centimeters per second, it's somewhat easier. M1 is equal to 1 kilogram and M2 is equal to 4 kilograms. We have to find final velocities V1 and V2. Okay. So this is a relatively simpler question, because you can see a lot of information is given. Okay. Already the directions are given for both V1 and V2 after impact. And to make things even simpler, V1 is perpendicular to V0, because it's saying that the first particle is deflected by 90 degrees. That means it goes off in a direction which is perpendicular to its initial velocity. Just assume this all is happening on a smooth horizontal surface, so gravity doesn't play a role. Normal reaction balances gravity and there's no friction. So imagine these are two bodies which are moving on a smooth horizontal surface, and the impact happens in this way. So as you can see, a lot of useful information is given, and also the information is such that the solving of the equations will be easy, because V1 is perpendicular to V0 and V2 is given at an angle of 37 degrees with respect to V0. And also the second body is initially at rest. So our momentum conservation equation is going to be quite simple. And by solving the momentum conservation equation itself, we will get the values of V1 and V2. Okay. So just note down this part and try to make the diagram of the impact that happens between these two bodies. Try to make the diagram of the impact with the collision impulse acting and the final velocities, how they will look in the diagram after the impact. Once you do that, we'll see that from that diagram, if you got the diagram correct, then it's going to be quite easy to apply the resolution of vectors in component form and do the momentum conservation. Okay. So at least try to make the diagram. I'll put it up in a minute. Okay. Okay, right, people. Let's understand the answers. Okay, Abhinath, I'll check your answer. So if we compare the picture before impact, so now let's put in the values here. M1 is 1 kg, M2 is 4 kg, V0 is 12 centimeters per second or whatever. Sorry, 15 centimeters per second. Yeah, now if, yes, very good, Manav. So both your answers are correct. I'll just verify the values, Manav and Adinath. Okay. So now if we compare this situation with what is happening after impact, so it's given to us that this one's velocity is in this sort of direction. It's perpendicular to the initial velocity. And this one's direction of velocity in this sort of direction, where this is making an angle of 37 degrees with respect to the direction of V0, which was this line. So if we take this as our x-axis, so now after impact, we can see that V1 is along the y-axis. So the collision impulse which is acted like this, that must have acted at an angle of 37 degrees to the x-axis. So anyway, so momentum conservation will tell us that M1 V0 is equal to M1 V1 plus M2 V2. So when we write this in component form, this will become M1 V0 I cap. This will be M1 V1 J cap plus M2 V2 will have to write in component form like this: cos 37 I cap minus sin 37 J cap. So when we substitute this, we will see that this will become 1 into 15 I cap will become M2, which is 4 into V2 into cos 37, which is 4 by 5 I cap, plus M1, which is 1 into V2, which is unknown, minus 4 into V2, sorry, M1 P1, not V2. Just a moment. Yeah, so this term here, it should be V1, not V2. So M1 V1 J cap minus M2 V2 sin 37. So that is 3 by 5. This whole thing into J cap. So now when you compare the X component on both sides, you have basically M1 V0 should be equal to M2 V2 cos 37, or basically that means that 15 should be equal to 16 by 5 V2. So that gives us the value of V2, that it is 75 by 16 centimeters per second. Okay. So correct value, Adinath and Manav. And when you compare the Y component, yes, tell me.
So how do we know that M1 is deflected up? It might have deflected down, right?
But that you can see in the collision, na? That the original diagram, the way it was made, is moving like this, na? And it's hitting something which is over here. So after impact, how will it deflect down? Because the impact impulse is in this direction. Na? Got it, na?
Yes.
So that is giving us the hint that it's going to deflect upwards and not downwards. Okay, along the y component, we have 0 on the left hand side. Right hand side, we have m1 v1 minus m2 v2 sine 37. This is what will tell us that 1 into v1 is equal to 12 by 5 v2. We'll substitute this value and our v1 will come out to be 12 by 5 into 75 by 16. So v1 will come out to be 45 by 4 centimeters per second. Okay, so this is the simplest level, or you can say the most basic level of question you can get for oblique collisions, where just the momentum conservation is giving you the required number of equations, because here we require only 2 equations. The directions were already given to us in the question, 90 degrees for this one and at 37 degrees for that one. So we just had to find the magnitude of v1 and v2. So for that we needed 2 equations, and they were coming from the individual component terms of the momentum conservation. Now eventually we'll see that at more advanced level questions, we will require more number of equations to be framed, and we might have to use, if the question gives us the value of coefficient of restitution, we'll have to use that and all that. Okay, but in this question we are not worried about that, because neither coefficient of restitution was given nor it was asked. We just had to find the final velocities based on the values of initial velocity and the angles which were given. Okay. So this is your common type of question at the JEE mains level. Yes, we can find Adinath, and I'll explain eventually how to find E also. Okay. But first we will do another example question. Then we'll see how coefficient of restitution is worked out in these kind of oblique collisions. Okay. So we'll come back to this example also to calculate the coefficient of restitution. But first I want enough practice to happen for the application of conservation of linear momentum through some simpler type of questions. Okay, so let's first look at that. Okay, so this time we have 2 identical spheres or identical discs or whatever, okay, which are on a smooth horizontal surface. And once again, the second one is at rest. So A and B are identical discs, mass M equal to, let's say, 2 kilograms and radius R equal to whatever, let's say 4 centimeters each. Okay, on a smooth horizontal surface. Now, A makes an oblique collision with B, which is initially at rest, such that it deflects by 30 degrees at a velocity of V. Okay. And B starts moving with a velocity VB such that magnitude of VB is equal to magnitude of VA. So given that V naught is equal to, let's say, 10 meters per second, you have to find the magnitude of VA or VB. Okay. The angle between the vectors VA and VB. And we have to also find the magnitude of the collision impulse. Okay, so let's look at this question next. So just again make the vector diagram for the impact and try to figure out how we can get these things here. So here again, two informations are given, but they are given in different way. Here, instead of giving the fact that the two angles are known, here one of the angles is given, that A deflects by 30 degrees, and the second information given is that B and A's final velocity are of same magnitude. Okay, so those are the two informations given. So using those two informations and using momentum conservation, we will find out the magnitude of this final velocity, and we will find out the other things, the angle between the final velocities and all this. So all this is about actually application of component algebra in vectors, nothing else, a simple two-dimensional component algebra. Yes, very good, Adinath. That's correct. So we'll see that the answer that we'll get over here on solving is that the magnitude of VA is equal to the magnitude of VB will come out to be 10 by root 3 meters per second, or V naught by root 3. And the angle between VA and VB will be 60 degrees. Now just work out the impulse also. In the meantime, let's discuss this question. So equal masses. Now what the question is saying is after impact, A goes off with a velocity like this. Let's say B goes off with a velocity like this. Now the information given to us here is that this angle is 30 degrees. As of now, this angle is unknown to us, but magnitude of VB is equal to magnitude of VA. This is so by using momentum conservation, we can see that we take this as our x-axis and this as our y-axis. Collision impulse will simply be m into v2 or m into vb in magnitude. Okay. So it will be 20 by root 3. I'll explain. Okay, just let's work this out first. So conservation of momentum. So let us see that along the x-axis, we have mv0 is equal to mva cos 30 plus mvb cos theta. So this gives us our equation that root 3 by 2 va plus vb cos theta is equal to 10. Okay. Further, we know that va is equal to vb. So let that value of va equal to vb be v. So this becomes b into root 3 by 2 plus cos theta is equal to 10. That becomes our first equation. And now along the y-axis, our conservation of linear momentum initial is 0, final is mva sine 30 minus mvb sine theta. So this tells us that va sine 30 is equal to vb sine theta. Now using the same fact that va's magnitude is equal to vb's magnitude, which is v. So we know that sine theta will become sine 30 degrees. So theta is equal to 30 degrees. So this is what our second terms. Second piece of information is telling us this. So now we substitute this in equation 1. So we can see that v into this is equal to 10. So this gives us v is equal to 10 by root 3. So magnitude of VA is equal to magnitude of VB is equal to 10 by root 3 meters per second. And also now the angle between VA and VB that we can pick up. So this angle is 30 and this angle is also 30. So the whole angle between A and B therefore becomes 60. Okay, now if we also look back to understand the impulse picture just before impact. So that must have been like this, that the impulse always acts along the center to center line. So that line only here is this one. It is at theta to this, because if you look at the impulse acting on B because of A and the impulse acting on A because of B, they are equal and opposite. So the magnitude of this impulse is equal to the magnitude of this impulse, equal to J, suppose. Okay. Now for the body B, this impulse itself is equal to the final momentum. So the magnitude of J is mv, which is so the magnitude of the collision impulse is so much. So hope this is clear, Adinath.
Yes, sir.
Now we can also use this fact that the magnitude of or the impulse acting on A because of B is equal to the final velocity momentum of A minus the initial momentum. So this will also give you the same result, but it will be a little bit more lengthy. So yeah, Adinath, there was no particular use of the radius here. Okay, it was just to show that they are identical, that they had equal radius. That was an unnecessary piece of information here. Now in this question, what we'll do is we'll calculate the coefficient of restitution. Okay, now let's understand in this, we add one more part to it, that let's calculate the coefficient of restitution. So let's add a fourth part. How much is this? Let's see. Okay, I'll just give you some time to write this down. Then we'll come back to the coefficient of restitution concept. Okay, so let's work out the coefficient of restitution. Yeah, it's correct, beta. The value you got, Adinath, is correct. So let's understand how we can, first of all, find out the approach and separation velocity, and from that, the coefficient of restitution. Okay, how we will implement those concepts here. So we will look at a situation where this is suppose just before impact. Okay. And we are comparing this with the situation just after impact. So just before impact, we know that the velocity vector, just a moment. Yeah, we know that the velocity vector of A is along our x-axis. And that is making an angle of theta with respect to the center to center line, because that is the line along which the impulse was acting. So this angle was theta, which we had worked out to be 30 degrees. Okay. So now we can understand in this, what is the approach velocity? It is the component of A's velocity towards B's center. So it is V naught cos theta. So it is 10 cos 30 or 5√3 meters per second. Okay. Now after impact, we can see that the velocities have become such that E is going off with a velocity in this sort of direction, and B is going off with a velocity along that center to center line. So with respect to the x-axis, now we can see that this angle is 30 degrees. This angle is also 30 degrees. So if we analyze this diagram a little bit more, we can see that B's final velocity is along the center to center line, but A's final velocity is somewhere like this, where this angle, this total angle is 60 degrees, the angle between the two vectors. So here, what is the separation velocity? We can see it is dB minus the component of A's velocity towards B. So it is V minus V cos 60. And V was how much? It was 10/√3 into half. So it is 5/√3 separation velocity. So now from this and this, we can see that the coefficient of restitution, which is this ratio, is one by 3. So just check your calculation once, Dinath. Why you're getting this as 2/3? Check the steps carefully. So this is how we find out the approach and separation velocity, first of all. Okay. Remember, the approach velocity is the relative velocities component along the line joining the two particles. So here by line joining the two particles, we mean the center to center line. Okay. Whereas separation velocity is again the component of component of relative velocity along the line joining, but that will be such that the two particles are separating. And approach case, it's such that the two particles are approaching. Okay, so this also becomes an important part of the analysis in this type of questions. Okay. In fact, at a more advanced level, next we will see questions where less information is given directly, like angle and all that, and we have to actually figure out more equations using the coefficient of restitution given. Here we were able to find out VA, VB, and the angle was given and all that. So we actually found out the value of coefficient of restitution. Now you can get another question where E is given to you, whereas the angle is not given, and we have to use that information of E as an additional equation. So those are the more advanced type of questions involving oblique collisions. So we'll come to them. Okay, once to answer your question, how we know that VB is along the center to center line. So that is where the impulse picture comes in. B was at rest initially. Na? Okay, so the moment you understand how B has started moving, it has started moving because of the impulse that acted on it. Na? And the direction of that impulse was along the center to center line. Understood this now? No?
Yes, sir.
Okay. So because the impulse acting on B because of A, that is only giving it the momentum. B was at rest in the first picture. That's why. If B had also been moving, then we could not have said this. Okay. So impulse on B is equal to its final velocity. I mean, final momentum. So that's why we know that VB is along the center to center line. In fact, that center to center line, we can call it the line of impact. This line here, or this line here. This is the line of impact. That is the center to center line. So the collision impulse acts along that line. Okay, now next we'll discuss one very important theorem related to this type of oblique collision. So we will discuss even the proof of the theorem, but this theorem is very useful for solving certain types of questions directly. So whenever we have the situation that a certain body or a particle makes an oblique collision with another particle of same mass at rest, okay, then what will happen is, if the collision is perfectly elastic, then after impact, the final velocities by definition, or according to this theorem, the final velocities will have to be perpendicular to each other. And we'll see the proof of this also, why this happens. So if a moving particle or body makes a perfectly elastic oblique collision with a stationary body or particle of same mass, then the final velocities are perpendicular. So this is the theorem. Okay. Now let's see one simple way of proving this theorem. Okay. So this is one statement we are getting from the conservation of linear momentum. Now another statement that we can write is conservation of kinetic energy. That is the other way of interpreting the nature of perfectly elastic collision. That's the other definition of perfectly elastic collision. So from equation 1, the magnitude of V naught is mod of V1 plus V2. And from equation 2, V naught is square root of V1 square plus V2 square. So this now implies that mod of V1 plus V2 is equal to square root of V1 square plus V2 square, which can only mean one thing, that V1 is perpendicular to V2. Okay, if you just go back to triangle law of vector addition, okay, you'll realize that this is the condition for perpendicular vectors, that mod of A plus B is equal to square root of A square plus B square. So this is one simple way of proving this. We'll see another way of understanding this result also, using the fact that separation and approach velocity are equal, or coefficient of restitution is 1. But the simple way of understanding this theorem and remembering it is like this. Okay. Now, more important than the proof for us is to remember this theorem, so that whenever this type of question comes involving this special case, that the masses are equal and the collision is perfectly elastic. Both are necessary conditions, that the oblique collision should be between equal mass particles which are colliding in a perfectly elastic manner. Only then, but then the important case becomes that the final velocities are perpendicular. Okay, so make a note of the theorem and its proof first. Then we will see how to implement this in questions. We'll see that remembering this theorem really makes questions which are based on this concept very easy to solve. So it's an important trick to remember. Okay, people, so let's see a question based on this. So now we'll make use of a question where geometry comes into place. So, the given radii of the two discs or whatever, they will play an important role. Okay. So now let us say that this one's velocity vector along this line, such that if we extend that line, it is at a certain distance from this one's center. And that perpendicular distance, it is called the impact parameter. So again, here, A and B are identical discs of mass equal to this time, let's say 1 kg each, and radius again equal to 2 centimeters each. Now, A's velocity V naught has a line of action which is at t equal to, let's say, 2√3 centimeters. A perpendicular distance from B's center. So this D, it is called the impact parameter. So what you can understand here in general is that if the impact parameter is 0, it would have been a head-on collision. If the impact parameter is greater than 0 but less than equal to 2r, then it is an oblique collision. And suppose the impact parameter is greater than 2r, there is no collision at all. There is no contact, just goes off. Okay. So in general, that is about the impact parameter. Now, if E is equal to 1 for this collision and V naught is again 10 meters per second, find VA and VB, that is the velocities after impact. So again, this whole situation is on a smooth horizontal surface. So now we'll see that the information given about the relationship between impact parameter and the individual radii, that will give us some geometrical picture to understand how much the angle will be of the line of impact with respect to V naught. So we will use that, and we will also use the special theorem that we've discussed above, that if the masses are equal and the collision is perfectly elastic, then the final velocities are perpendicular to each other. So by using that theorem, we can see this question is very easy to solve. It can be solved within a couple of minutes. But if we don't use that theorem, then also we can solve it, but we'll end up basically deriving that theorem. So the whole question and the data solving is going to take more time. So that's why this special case, being able to use the theorem becomes an important trick for solving these type of questions.
Sir,
Yeah, what were you asking, beta? No, D has to be greater than 2R, beta. I'll explain why. See, just understand the diagram. If no contact is happening, then the situation has to be like this, that this goes off like this. So you can see now the impact parameter at that time, this D is becoming more than 2R. Whereas if they are coming in contact, then you can see that this D is less than 2R.
Yes, sir.
Okay. And if D is equal to 0, you can see that it's a perfectly elastic collision. I mean, head-on collision. Not perfectly elastic, but head-on. Yes, very good, Adina. That's correct. Good, Manav. Yeah. So you would have understood, I guess, that the angle of the line of impact with respect to V naught is how much? It is 60 degrees, right? You're getting that from the diagram. Just draw the diagram when they are coming in contact. Okay, so you will see that the relationship between the center to center distance, which is 2R, and the impact parameter, which is that perpendicular distance D given, that relationship will give you that angle. The angle between the line of impact, that is the center to center line, and the velocity vector V naught. So that angle you should be able to calculate to be 60 degrees. So when you do that, once you do that, then the collision becomes easy to solve, because you know that V naught, B is going to move along that line. So B is going to move at 60 degrees to V naught. And then use the theorem that if B moves at 60 degrees, then A has to move at 30 degrees above, so that A and B are perpendicular to each other. Okay, so let's see the solution of this. So once again, if we compare the situation just before contact, with the situation during contact, and then the situation after contact. So just before impact, if this velocity is along this line, whereas this center to center line this is 2r, the center to center line. Whereas if we drop this perpendicular here, we can see that this distance is d. So if this angle is theta, you can see here that theta is sine inverse of d by 2r here. Okay, so that is becoming sine inverse of 2 root 3 divided by 2 plus 2 or 4. So that is sine inverse of root 3 by 2. So that means this angle is 60 degrees. This theta is 60 degrees. So the collision impulse that is acting along this 60-degree line, like this, with respect to the initial velocity of that one. This angle is 60 degrees. If we take this as our x-axis. So now we know that the final velocity of B will have to be along that. So we know that VB will have to be at 60 degrees with respect to our x-axis. So we also know indirectly now that VA will have to be at 90 minus theta or 30 degrees like this. Because the collision is perfectly elastic. And mass of A is equal to mass of B. Therefore, BA is perpendicular to. So we're making use of this theorem. Okay. So now if we just write momentum conservation, okay, we can see that BB will actually become V0 cos theta and VA will become V0 sin theta. So these will be the final velocities. This is the magnitude of the collision impulse. So I have written these by actually taking components along line of action or line of impact and the tangent. So I'll show you what the line of impact here is. That is this one. This is the line of impact. And this one perpendicular to it, that is the tangent. So in this diagram also, this is the tangent and this is the line of impact. So I have done the resolution of vectors not along x-axis and y-axis, but I've done along line of impact and the tangent, which are mutually perpendicular lines, of course. That's how I've got this actually. I've got this result like this because BA is along the tangent because it's perpendicular, and VB is along the line of impact because it's along J. So an extremely easy way to solve the question by using this trick. Okay, people. So with this, you should be able to complete HC Verma this week fully.
Sir,
Yes.
how did you get BB is equal to V naught cos theta?
But I was not able to hear you. Can you speak a little bit louder, please?
Sir, how did you get VB is equal to V naught cos theta?
So what I've done now, I have resolved these vectors along these two lines, the line of impact and the tangent line. Understanding now?
Yes, sir.
So this is my tangent axis and this is my line of impact. So in that, what is my V naught's direction? V naught's direction is like this. So this angle is theta. Okay. And after impact, what is happening? If this is the tangent line and this is the line of impact, then one of the particles is moving along this line only, VB, and the other one is moving along VA. Okay. So when you compare this and this, you can see that V naught's cos component only will become this. Okay. So momentum conservation will tell me that mV naught cos theta is equal to mVB. This is along line of impact. And mV naught sin theta is equal to mVA. It's along the tangent.
Oh,
Okay, so if we don't know the theorem, then we'll have to use that approach velocity is equal to separation velocity. So we'll have to assume some general direction of VA. Okay, without knowing that this angle is 30 degrees. So we'll take this angle as some unknown, alpha, beta, something like that. And then we'll calculate approach and separation velocity. Approach velocity is of course V naught cos theta. So we can see it as 5. But separation velocity then will become VB minus or plus some component of VA, depending on how we have done it. So we'll have to use that as an additional equation along with momentum conservation. So we'll get the third equation, but we'll have the third variable. Apart from VA and VB, we'll also have that angle. Instead of 30 degrees, it will be some unknown angle. So to resolve the three variables, we'll have to use the three equations. So the third one will be the using the coefficient of restitution equal to 1. Okay. Or we can even use kinetic energy conservation, but that will become even more lengthy because you'll have to write it in terms of components. So that is why I said that it's important to remember this theorem. Okay. All right. So as I was saying, with this, we complete this chapter. Next time also we'll discuss, like I have a lecture on Sunday with your batch, and it will be a live lecture from Nerul Center. So those of you who are of non-integrated batch and Nerul Center integrated batch for Red House, you can attend the lecture live from the Nerul Center on Sunday, 11 to 1, I think the lecture is. The lecture will also be streamed for other center students to watch online. Okay. So anyway, in that we will do more practice questions based on oblique collisions. We will see situations where the collision is not perfectly elastic. So E's value is given. So how to use the value of E in solving and all that. And then we'll come to the last part of center of mass chapter or system of particles chapter, which is variable mass system. Okay. But using this information that we've learned here, you can go ahead and complete HC Verma almost fully. Okay. Also, I'll be sending you the answer key of the module separately because the answer key is not given for module 3's system of particles exercises. So we'll be publishing the answer key separately and sending it to you soon. So please start working on the exercises from the module also. That's it for today's session, people. Wish you all the best.
Thank you, sir.
Thank you, sir. Bye.